Okay, time to get started. Boy, we have a lot to cover today. We're doing invisible light. I want to finish up a little bit on visible light, a few things I want to say. Let me just mention that next week is spring break. Homework is due today. There is no homework due next week on spring break. You're on spring break. Now, some of you are under the mistaken impression that spring break is a week and a half, or maybe 2 weeks. Some of you may even be planning on skipping this Thursday to get a running start on spring break. You are not to do that. You are required to come to class on this Thursday. I want you to know that. However, there will not be any quiz this Thursday, and I won't be taking attendance, but you're required to come. You'll miss a great lecture if you don't show up. That will put you at a disadvantage compared to the people who do. So don't stretch your spring break and skip class on Thursday, and I make no promises about quizzes on Tuesday. So have a great spring break, but take it easy. Don't come back from spring break needing a break. Okay, that's the spring break 1.5. It's supposed to be just 1, not 1.5. No homework due next week, but homework due today as usual. I wanted to say a little bit more about blurring. We just handled that very quickly last time. It becomes a major issue in photography, in cameras, in spy satellites. Let's look at the pinhole camera. Pinhole camera makes an image by having a tiny little hole. Light from the eye comes from the hole and exposes just this part of the film or CCD. Light from the feet, that's a funny looking guy, comes this way and here, so you get the upside down image. And don't forget, when you get your film back from the camera developer, to turn the image over. It was taken upside down. Okay, so here's the image. Now, this depends on the fact that light goes in a straight line. If the light from the eye went like this, and like this, the eye wouldn't be here, it would be here, and here the light would be spread out. Now, unfortunately, light does not go in a straight line. Light is a wave. The wavelength is very small. And so if the hole is very large, compared to the wavelength of light, there are the crests of the waves coming in, then it comes through, and it bends a little bit around the edges, and that little bit of light contributes to blurring. Actually, it winds up bending everywhere, but not very much. Not if the hole is large compared to the wavelength. The formula for blurring has this fraction in it, the wavelength divided by the diameter of the opening. If the wavelength is very small compared to the diameter, then this fraction is tiny, and the blurring is tiny. If the hole is really small, comparable to the wavelength, then the blurring is like 1. And this blurring says if you go 1 meter away, that's the R. If you go 1 meter down from the hole, the amount of blurring you'll get will be 1 meter if the wavelength is comparable to the opening. In other words, if the opening is really small. So for a really small opening, the wave just comes out like this. And some of the light from the eye will wind up going this way, some this way. The light of the eye will be spread all out. It'll be blurred. It won't be very useful. So you have to have, you can't have an opening that's too small. Now here's the key issue in all of this. Even if the opening is large, you still get some blurring. It's just tiny blurring. But tiny blurring can kill you. Imagine you have a camera in space, you're an astronaut, you have this camera, you have not a pinhole, but you have a lens. That lens now becomes this diameter. The wavelength is tiny. It's a 1/2 micron. This lens may be this big. And so the blurring is really tiny. But you're looking for something tiny on the surface of the Earth, like a license plate. You're trying to photograph the license plate. You still get a little bit of blurring, but that little bit of blurring can destroy what you want. So last time I had two examples, they're also in the book, showing that if you're 200 kilometers up and you have a huge lens, 2.4 meters, this is the size of the Space Telescope, this multi-billion-dollar project. 2.4 meters is like 10 feet. That's the size of the lens. They actually use a mirror instead of lens, but it still converges the light. And so the blurring is really tiny, but a tiny bit of blurring, when you're trying to magnify it to be able to read a license plate on the ground, what I showed, if you use this equation, put this as 200 kilometers, let the diameter be 2.4 meters, and the wavelength be tiny, half a micron, a half times 10 to the minus 6 meters, this still says that the blurring, when you look at something on the ground, is about 4 centimeters. Which means if you have the Space Telescope in a low orbit, and you're looking straight down, your license plate will be so blurred it'll be hard to read, but you could probably still read it. Now, space satellites, of course, don't stay there. They're always moving. It's rare that they're directly overhead. So when you read that you can read license plates from space, it's basically not true. You could have a bigger telescope if you want to put up instead of, let's say, a $10 billion space telescope, you want to spend $1 trillion. Well, we've never spent that kind of money on anything in space. If you put it further away, it's even worse. I once designed for NASA a 100-meter diameter lens in order for them to be able to put it up in geosynchronous orbit. Even that isn't enough to read license plates. They made a painting of it. I don't know if I think I have it on my website. 100 meters is like a football field, and you couldn't fill it in, so I made it into what's called a ring aperture, which means the effective diameter is large, 100 meters, but you don't have to have all that mass in there. So this is the blurring problem, and it comes about because light is a wave. And because light is a wave, when it goes through an opening, it spreads out a little bit. And it doesn't spread out very much if the opening is large compared to the wavelength. But not spreading out very much still can blur things. This is why in the US defense war machine, there is more and more of an emphasis on airplanes, specifically on non-piloted airplanes, RPVs, remotely piloted vehicles. They're piloted, but remotely. If someone back in the US driving the airplane, and they, a radio link so they can see where they're going. The idea with these is you can have a small camera, but get really close. How small and how close is an interesting issue. Our Predator drone spotted Osama bin Laden. And it actually had a missile on board. It could have shot him. This was back shortly after 9/11. But at that time, the rules of engagement were you had to get presidential permission, and by the time they did that, Osama bin Laden was gone. The whole idea of whether you should shoot world leaders from a drone is an interesting moral and ethical and political and legal question that you should discuss. One of my essays has to do with the use of these things and the dangers that they can cause. It's not that hard to make. You could buy a little airplane, a toy airplane, that you can fly. It costs about $50, and you can fly it with a little radio, and you can make them even cheaper. And so amateurs can start using these things. It's an interesting danger for the future, this type of world, of war, of politics, of terrorism. But for just spying purposes, the fact is a small plane can get a lot closer. You're often better off doing that. I don't know if there are any hobbyists here who've ever put a camera up in a kite. That's not hard to do, a little camera. You can put a timer on it, put it up in the kite, have it pointing down, and photograph the ground from space. You could do it with a radio these days. You can put them on a little toy airplane and fly around and try to do that. These things aren't that hard to do. When done by the military, this is becoming more and more important. Our soldiers in Iraq and Afghanistan, have little planes like this that they can fly. Suppose they're doing some battle. There was recently a battle in Iraq in which they invaded an area where the insurgents are concentrated. But before they go in, they can send up one of these little airplanes, and it'll go over there, and it can look behind buildings. And this works better. In most cases, it is a better option than the spy satellite, because the spy satellite just zooms over, and maybe a day before it comes back to that same spot. I mean, it comes back an hour and a half later, but the Earth is rotated. So it's not over the same spot. You have to wait till the Earth is rotated all the way around before you get to the same spot. And spy satellites are very high, and they're very expensive. So the future of surveillance is probably not spy satellites, maybe airplanes, remotely piloted vehicles, and balloons, and things like that. So that's what I want to say about blurring. Obviously an important thing to know for future presidents. Now let's get into infrared and ultraviolet. I want you to know those terms. IR stands for infrared. This is the light that isn't quite visible. If you look at sunlight and you look at the amount of radiation, so this is the intensity, and you look at different frequencies, there's a certain intensity of visible light. This is green. And then the blue, there's not as much. And the red, there's not as much coming from the sun. And it drops off like this. And over here is the infrared, and there's not that much. And over here is the what's called the ultraviolet. These are the higher frequencies. By the way, higher frequency is a shorter wavelength. Lower frequency is a longer wavelength. For light, the wavelength times the frequency is equal to the speed of light. And this is the same. So if this is big, that has to be small. So sometimes you'll hear me talk about short wavelength light, ultraviolet, or long wavelength, infrared. Long is on this side because this is a low frequency. And the sun doesn't emit much of these. It emits some, and the amount it emits is very significant for our lives, but not enough for us to really develop eyes to use it. So we haven't. Our eyes work in this region, the so-called visible light region. But this light is there. The sun emits it, ultraviolet light. The ultraviolet light, because it has a short wavelength, we will learn in quantum mechanics, for which we start on next week, that the high-frequency short wavelength means the wave packets contain a lot of energy. They contain a bigger burst of energy than wave packets here, here, or here. This will be important. So ultraviolet radiation delivers its energy in big bursts compared to visible light. The bursts are big enough that they can damage your DNA. They can cause mutations, much more so than visible light. That makes the ultraviolet radiation somewhat dangerous. In fact, it's possible that without some shield, so that most of the ultraviolet radiation from the sun, even though it's not that much, most of it doesn't get to the Earth. And if it did, it's possible that advanced life involving DNA and RNA never would have evolved on the Earth, because this stuff is so damaging. We need an ultraviolet shield to protect us. We, in fact, have an ultraviolet shield. It's called the ozone layer. And we'll be talking more about this soon, but you go up to about where the thunderheads go, you run into the ozone layer. I've mentioned this before. That ozone layer is actually created by the ultraviolet light. The ultraviolet light coming in from the sun, there's not much, but there's some there, enough to do damage. Not enough to see very well if we could see it, but enough to do damage. It comes in from the sun. When it runs into the atmosphere, most of it gets through to the ground. Some of it gets stopped by the atmosphere. When it runs into oxygen molecules, it rips them apart, taking O2 and turning it into two O's, separate O's. So your molecule of oxygen, O2, gets broken apart by the ultraviolet radiation. Now you have this O floating around. It sees another O2, and it's attracted, and you get an O3. That's called ozone. Ozone happens when you break apart an oxygen, and those two individual oxygens attach themselves to molecules to make O3s. Now, it turns out that O3 is extremely effective at stopping ultraviolet light. It really absorbs it a lot. So you wind up creating this ozone, and then the ozone forms this layer up in the atmosphere, and it stops most of the ultraviolet light from coming in. It's called the ozone layer, and there was a while when we were seriously worried that we were destroying the ozone layer. That's one of the key international issues in invisible light, is the issue of the ozone layer. You read about it in the book. We'll talk about it some more. Infrared radiation is very low radiation. It's very low energy per packet. It doesn't cause cancer as near as we can tell. When you have infrared radiation hitting you, you don't see it, but it is depositing energy in your skin, and so you feel the warmth. Now, that would also be true of ultraviolet radiation, but if you're exposed to enough ultraviolet radiation to feel warmth, it would be truly dangerous. Infrared radiation, sometimes you make infrared radiation. It's called a heat lamp. As you get down to shorter wavelength, they have what they call the far infrared, FIR. That's down here. This is the IR. FIR is even lower frequency. 10 times lower than the ordinary infrared. This has a fascinating story, and my first really dramatic experience with the far infrared. This is very low frequency, so it has a long wavelength. Visible light is half a micron. The far infrared is typically 5 microns, 5 to 10 to 20 microns. That's the far infrared. 10 to 20 times longer than visible light. Anyway, my really dramatic experience was this, as described in the in the reading this week, was one time when I was invited to go down and watch the Border Patrol at the Mexican border catch illegal aliens. And it was truly a fascinating experience, but there were a couple of surprises. The most dramatic surprise was their use of the far infrared. I'd read about this, but I'd never seen anything like that. So here we are, sitting. It's about an hour before sunset. We're up on a hill, quarter mile from the Mexican border. There's this fence, because we're right in Tijuana. And get the ordinary binoculars, and you see all the Mexicans waiting on the other side of the fence. Border Patrol says, well, those are the ones we caught yesterday, and now they're waiting to come over again. So, well, what good does it do? And they say, well, it costs them more money, because money? Why does it cost money to go over the border? Oh, they can't go over the border themselves. I mean, yeah, they can climb the fence, but then what do? So they have to find their guide. So they hire a guide, and that's what costs money. And they meet the guide on the other side of the fence, and the guide will take them along the trails, trying to avoid the Border Patrol to get into San Diego. And so that costs money. So they have to pay again when they go back. So when do they go over the fence? Well, they wait till sunset. Okay. So we waited, and they're selling tacos and things. It's quite a business on the border. All these people have been waiting around for a day to go over again. And the sun's getting down, it's getting dark, and I'm watching it. And suddenly this one kid runs to the fence and climbs over it. He sort of just did it on his own, I guess, or maybe it was a signal. But at that point, everybody thought, oh, it's time to do it. So everybody started going. They're all climbing the fence. And I'm watching the Border Patrol sitting there, climbing the fence. And they get on the other side, and they run into the hills. Border Patrol's sitting there. I'm sitting there. They're waiting. Sun gets lower, lower, lower. Gets really dark out. I said, why are we waiting? He said, oh, right now, they're all congregating. They're meeting their guides. And they won't try moving until later. We'll get them when they come up here on the roads. Okay, we're waiting. It's getting dark. I can't see a thing. I'll use the infrared binoculars. So I go over, and they have this set. It's a laser I'm looking at. Anyway, go over, and they have This pair of binoculars is a big, expensive pair. It has liquid nitrogen cooling. Back in those days, you're required to cool it. You'll understand why in a moment, why they have to cool it. And I'm looking, and now it's really pitch black out. No moon, no anything, can't see a thing. I look at these infrared binoculars, and what do I see? I look around and I see a bunch of little glowing things there. And I look at it, turn up the magnification, it's people. And they say, yeah, look around, you'll find the groups that they've congregated. So I'm looking around, and there they are, people glowing. Now, what's happening here? What's happening is that you, right now, are glowing. I turn out the lights, you won't see it. The reason is you're glowing in the far infrared. Why in the far infrared? Well, remember the reason you're glowing is because you have a certain amount of heat. Heat means your molecules are all shaking. Electrons are shaking faster because they're lighter, and they shake with similar energies. Learned that the second week. So the electrons are really shaking. When they shake, they make waves. Those waves travel out. They're electromagnetic waves. So you are emitting light. At your temperature, which is about 300 above absolute zero, the waves that you emit are mostly in the far infrared. You can't see those. But you can sense this. So here's something I want everyone here to do as an extra homework assignment. Okay, so do this. You may choose to do it during spring break. Pick some time. I want you to sense the warmth, which is the infrared radiation, when you get close to somebody else. Best done with the face. So pick some opportune moment and get really up close to another person's face. The lips are particularly sensitive to this. I think it has something to do with a natural instinct to reproduce. And as a result, this sensation, this heat sensitivity, is actually, believe it or not, pleasurable. It's interpreted by your brain as something that's good to do. So I want you to do that before the next Tuesday lecture. Who knows, maybe it'll be a pop quiz on this issue. But I want you to sense this. I want you to sense having someone up close and feel their... No, not yet. Not yet, okay? Not during class. I'll do this later, okay? So, pit vipers are very good at this. In fact, many animals do this. The pit viper is a kind of a snake. And they have very sensitive infrared sensors. They're not like eyes. They don't see anything, but they can sense the warmth. So they like to sit on animal trails, typically mice trails. And they'll sit there in the total darkness. And a mice will come by, and they will sense the warmth and go, yeah. And that's how they hunt, using the infrared sensors. Mosquitoes have a similar sensor. They sense your body because you're warm. There's several sensors that mosquitoes apparently have, including water vapor, so they sense the water vapor coming off your skin. They also sense the warmth. So, you know, if you want to avoid mosquitoes and you're backpacking, just pack ice on your skin, but watch out for the water vapor. But they sense the warmth too, but you too can sense the warmth. These infrared sensors, just to finish the story, I was watching these groups, and then they would start marching together and stringing out into a line, led by their guide. And then the guide would lead them over the trails, and the Border Patrol would then go and meet them. And their expression when they're met is, oh, drat. And they politely allow themselves to be arrested and put in the truck, and they would be interviewed and cataloged and logged and sent back to Mexico. They had the money, they'd try it again, a third time or a second time, and so on. I asked this is nothing to do with physics, but I was curious about this. It seemed like a frustrating job to be Border Patrol. You catch these people, you send them back. They come over again. You catch about 1/10 of them, so the odds are pretty good they'll make it the second time. Isn't this a frustrating job? I said to the Border Patrol. He said, well, it's a job. I do my work. I said, what do you think of these people? He said, oh, they're such nice people. He said, they never give us a hard time. We drive up, and they don't run. They just come, and they get arrested, and we take them back. And, he said, they're all here just to support their families back in Mexico. They come over here, and they work really hard. I found this very interesting for the Border Patrolmen to express this to me. They work really hard, and they send essentially every penny they earn back to Mexico. And I wish my son had their kind of work ethic, he said. Well, that was an odd thing from a guy working at the Border Patrol. But anyway, that was his job. And it was fascinating watching these people. Now, this kind of far infrared is really useful. I mean, yeah, question, Zach.
Yeah, if you can see them so easily with these far infrared goggles, binoculars, then how come 90% of them will get
Okay, the question is, if you can see them so easily with these binoculars, how come 90% of them get through? And the answer is simply, Border Patrol didn't have enough people to get everybody who was coming. It's just a matter of numbers. They would just get the easiest ones. So this technology, I remember when, right after 9/11, when Osama bin Laden was hiding in the mountains and the newspapers were reporting that snow had fallen, and this was going to make it extra difficult to find Osama bin Laden. My reaction was, what? No. This makes it extra easy to find Osama bin Laden. Snow is cold. Cold things don't emit as much radiation. In fact, as I'll indicate, it's in the text, if you double the temperature, let's say from 600, you're at 300 Kelvin now, 300 above absolute zero, 300 and something. If you go from 300 to 600, the amount of radiation doesn't double. It doubles and doubles. It goes up by the fourth power. So fourth power means if you double, and then you double, and then double, and then double. So it's not. It's four doublings. So fourth power means if you double the temperature, the amount of radiation goes up by a factor of 16. So as you get a little bit warmer, the radiation goes up a lot. When you have snow on the ground, it emits very little radiation. When you have a terrorist hiding in the snow, and you are in one of these drones that flies overhead, and you have an infrared detector, then the things really stand out. Even if you're looking at caves. Now, cave mouths, the mouth of a cave is usually warmer than the snow, so you can spot caves. But if people are in the caves, then they really glow. They're like flashlights lighting up on the hillside, the caves that have people in them. So this is an important part. It's become an essential part of military technology. In fact, our soldiers have now adopted the motto, what used to be the motto of the Special Operations, has now been adopted by the entire U.S. Army. It's, quote, ready? We own the night. And what they mean by this is that most of our soldiers are fitted out with some kind of night vision. Not all of them are far infrared, but some kind of night vision. And more importantly, they're trained at night vision. So they expect to fight their battles at nighttime when nobody else can see. It's a little bit like the pit viper who does its hunting at night when the mouse can't see it as well as it can see the mouse. So we own the night has become part of this. Now, the forces that do this use two devices. One of them is simply what's called a starlight scope. Starlight scope is something that simply takes the little bit of light that's there and makes it brighter. And it does this through some technique that we'll talk about next week when we get to quantum mechanics. It's just a light amplifier. And I'm thinking of buying a starlight scope for when I go to Africa. So when we're out there at night, I can watch the lions stalking their prey with one of these things. I haven't bought this yet, but I'm considering getting that. But the far infrared is something else. In the far infrared, you actually can see the glowing person. I have some photographs on the web page. I may show them in lecture on Thursday for those of you who are here like you're required to be. Now there's something else in between the starlight and the far infrared. There's the near infrared. Near infrared, we don't emit much of that because it's too high a frequency. It's just barely not visible. This has lots of uses. The near infrared I have used to photograph my daughter and her husband-to-be when they were dancing in a movie of them dancing at night in a dark nightclub in Paris. You turn on this little movie camera, and you can't see a thing, but you look in the camera, and there they are dancing. It's in black and white. What's going on? Turns out the movie camera has a little light on it that emits light in the near infrared. It's like a flood lamp in the near infrared, but it doesn't bother anybody in the dance hall because they don't see it. But the camera is sensitive to this light. So it sees the people, the light comes back, you get an image on this, and then the image, of course, is then turned into, by using false color. It doesn't show it to me in infrared, it shows it to me in black and white. So I see the image. But it's detecting the near infrared using a lamp. This is a very common type of photography, using infrared flash or infrared lamps. Uses up a fair amount of energy. I have a camera now that has an infrared focus on it. If it's dark out and it's having trouble focusing, what it does is it emits an infrared beam and lights up the object in the infrared so that it can focus on it. And you can do that without disturbing the darkness, which you may want to preserve. Infrared detectors will notice the heat of your body. You go to wash your hands and you say, "Where's the knob?" And there's nothing there. And you put your hand and the water turns on. A little detector there that's hooked up like the Pit Viper to detect the infrared radiation of your hands, and then it knows your hand is there. You take your hand away, the water goes off. These are little infrared detectors. Some door openers work this way. Door openers work on various different ways. Some of them use radar to detect that you're there. Some of them use what's called a motion detector, which is like radar, but it looks at only things that are moving. Others will use the infrared, which is the fact that you're emitting. So I have a demonstration here. I have something here that I'm going to heat up, and I'll turn it on, and it'll start warming up. It's just like the tungsten filament of a light bulb, of an ordinary incandescent light. Incandescent, what does that mean? Incandescent, candescent probably comes from the roots of candle. It's glowing from the heat. That's what an ordinary filament light bulb has with a wire. Send electricity to it until that wire gets hot. Get hotter and hotter and hotter. The hotter it gets, the electrons don't have very much space to move. So if they're moving faster, they're moving at a higher frequency. You get them up to where they're emitting in the visible. You turn up the filament. The filament, as it gets hotter and hotter, first, it's at the relatively low frequencies that you can see. That's called the red. So the filament tends to emit red light. You get it hotter and hotter, and the white gets whiter and whiter. If you get hot enough so that you're emitting sunlight, so you have all the colors of the spectrum, you have to get up to about 6,000 degrees. Whereas just to see sunlight, you're at a couple thousand degrees, maybe 2,500 degrees. So the light works by heating up. All right, now I'm heating this thing up. I can feel it. It gives me a false pleasure. But I know better than to get closer. And as it heats up, it's going to glow. It's not going to get really super hot, and so it's only going to glow basically in the red. Some people like these lamps. They like the filament lamps because the color is a little bit redder, because it's not that hot. And so you take a lamp like this, and you're in the bathroom, and you turn on this lamp, and you see your skin, and your skin is a little bit redder, and you interpret that as being healthier. You turn on a lamp such as a fluorescent lamp that has a fair share of blue and green mixed in. It's more like sunlight, and you look at yourself and you say, "Oh, I don't look so healthy. Let's turn that light off. Let's put on the incandescent lamp." But just because it's redder, you can make someone look healthier. With rouge, people put on rouge because small children have very pink cheeks, and so people believe. By the way, I have a theory. I haven't really checked. I know that as I got older, in my eyes, before I had my lenses replaced, I had these cataracts, and I got the lenses replaced one at a time. I looked at my new lens, and I looked at that eye, I looked at that eye. Wow, the colors were so much more vivid when I had the lens replaced. I could see white was so much whiter. Wow, I didn't know white was that white. Eventually, I had both lenses replaced. Now I see colors, brilliant colors. But I have a theory that a lot of people don't do that. They don't have their lenses replaced. They're losing their colors. And I have a particular vision that some older women who no longer really see the red very brightly put on red makeup until they can finally see it. And you've probably noticed this with old women. They have this garish red makeup. But I suspect that's because they don't realize how bright it really is, or how bright it is to the rest of us. Okay, now, as you are heating up a filament, sunlight, if we look at the frequency, the brightest point is in the green. So here's sunlight. It looks like this. And here's the high frequencies are the blue, and then here's the green, and here's the red. And this is the amount of frequency. This is the intensity at different frequencies. And that's ordinary sunlight. If you take a bulb, a tungsten bulb, and you are running it at basically, it's not quite that hot, it will emit mostly lower frequencies, also less light. So a tungsten bulb may be something like this. So here we have the light bulb. Here we have sun. And look at the difference. You don't even see this light. This is in the infrared. The only light you see is this little bit over here. The result is most of the light that's coming out of an ordinary light bulb is invisible to you. Something like 13 or 15% you see. The rest of that energy is going to heating up the room. Not necessarily a bad thing to do, except you don't like it on a hot day. But if your purpose of the light bulb is to get light, you are wasting 85% of the energy. This is very important if you care about the cost of energy or the amount of energy that we are using. In contrast, if you take a fluorescent light bulb, something like 35% goes into visible light, sometimes even more. So for the same amount of electricity, you may get 2 or 3 times as much light from a fluorescent light bulb as you get from a tungsten. If you could see the infrared, you would see that, because that's where the energy is going. But most of it is, so what do we call this? We call this heat. Okay, turn this off now. What I would like to do now is have the lights completely turned off. Black, 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 all lights down. Down, down, down. And let me even turn this light off. Let me get my little flashlight here, here it is. So if I get lost, I can find myself. And let's see, if we could focus, ignore this for a moment. The prettiest thing today are those rocks. Now, I don't know how well the camera will do. Got to watch out for this rope so I don't strangle myself. Shining in on this thing here. But most of the light from the room is actually coming from that projector. Okay, are you focused in on this thing right now, right here? Yeah, there you are. So can you see it? No, you can't. Therefore, I ask for you, I bet my infrared camera will be able to see it. Let me ask you to turn the projector off, or block the lamp, put a piece of paper in front of it, or something just to make it darker. Okay. Now, the lightest thing in the room are those of you who have their laptops open. Would you mind closing your laptop window for a second? Hello? That's how you tell whether people are really paying attention. Okay, so now look at the glow here. Can you see the glow? Right, I'm over here. And right in front of me, you see the orange glow. If I were to get this even hotter, if I could, which I can't, this orange glow are the electrons shaking and emitting this electromagnetic radiation because of the fact that they're shaking. Same thing happens in a tungsten filament, except the tungsten filament gets even hotter. Okay, we have the lights back on now. You can open your computer again. Okay, lights on. That glow is what's sometimes called thermal radiation. You are emitting thermal radiation right now. Not a whole lot, but you're emitting your thermal radiation because of the fact that you are warm, except those of you who are dead. And even those of you are warm because you're at room temperature, but not as warm as those of you who are not dead. So this is thermal radiation. With a light filament, you heat it up even more. You double the temperature. Typically, you get up to 2,500 degrees. Now, here's the way the rule works. It goes as the fourth power. So if you're, right now, most of you are at about 300 and something degrees. This is room temperature. Everything in here is glowing. If you compare that to 2,400, let's say, the temperature of a light filament, okay? So this is about 6 times, 8 times more. But the energy emitted is 8 times 8 times 8 times 8. Now, if this were 10, it would be, yeah, let's make this 3,000, a hot light bulb. Then it's equal to 10. And then this number is 10 times 10 times 10 times 10, which is 10,000 times more energy, because you have to multiply itself 4 times to figure out how much energy it's giving out. That's why the sun is so much higher than the light bulb, so much brighter than the light bulb. Now, you can make the light bulb brighter by turning up the temperature, by getting it really hotter. You can make it the same temperature as the sun. The problem with that is the filament will melt. Now, this used to be something we would do. They were called flash bulbs. You get a light bulb where you heat it so hot that it actually emits light similar to the surface of the sun. That's very good for photography if your film is expecting sunlight. Your film, in your picture, your film will look very red. And you may have seen this. If you take a picture with ordinary film, but you do it with tungsten light bulbs, you'll notice that it's very red. Now, it's interesting and it's odd that when you see somebody in these light bulbs, they look a little bit healthier, but they don't look super duper red. And this is, as near as I can tell, part of our psychology. Our eyes can adjust. Our brain adjusts for this. When we see someone in these lights, they don't look that red. They just look a little bit healthier. Our brain makes up for the fact that the light is extra red and compensates for it. If for some reason we don't do that when looking at a photograph, maybe because of the outside room is ordinary light. The ability of the eye to do this is truly a remarkable thing. And let me just give an example of that. I don't know how many of you have ever used green sunglasses or orange sunglasses. Orange sunglasses are favorites of skiers. I used to think, orange sunglasses? I don't want everything to look orange. But this is supposedly good for the sun. You get more contrast because the shadows tend to be blue, and the blue light doesn't get through, so it enhances shadows. That was the idea of the orange sunglasses, or yellow sunglasses. So, okay, I'm a skier. I'll put on the orange sunglasses. Yeah, everything's orange. Yeah. And then you're skiing, so on, and then you look around, and you say, let's see, did I put on the orange sunglasses or the gray ones? I can't tell. Rather odd. Let me take them off. Woo, everything's green. I adjusted. My brain adjusted. It's sort of like adjusting for things upside down. It's amazing how your eye adjusts for this shift in colors. But in photographs, it doesn't, when you're looking at a photograph and everything else is normal, your brain doesn't adjust. And so if you take a picture with ordinary tungsten light, it'll wind up looking orange or red. And that's because the bulb isn't as hot as the sun. If you're a potter, I don't know how many people here have worked with a kiln, but as things get hotter, the electrons move faster. Since they're not moving any further, that means they have a higher frequency. That means the frequency increases. In fact, the frequency basically increases with the temperature. The frequency, we say, is proportional to the temperature. So as you go to higher temperature, it's a higher frequency. So here you have 2,000. Here you have 6,000. If you go even further, hotter than the sun, you emit a lot of ultraviolet radiation. The main peak becomes ultraviolet radiation. There are stars that emit ultraviolet radiation. The sun. If you take an object and heat it up to the temperature of the sun and look at the light coming out, you get basically the identical light you get from the sun. The good news is you can reproduce sunlight with a flash lamp or a super hot filament. The thing is, you don't want your filament to evaporate, to melt, so they will use tungsten and other so-called refractory metals that don't melt at these temperatures, but at these hot temperatures they react with the air. And so the only way to make this work is to cover the filament with a bulb, that's why we call them light bulbs, and put in a gas that contains no oxygen so they don't oxidize. They don't react with the oxygen at these high temperatures. So you could put a vacuum in there. You pump all the air out, or you can put in a neutral air that doesn't react. It turns out putting in a neutral air is better because it suppresses evaporation from the surface. So that's why a light bulb is called a light bulb. It's put in, you want to keep the oxygen away from the filament. But if you get hot enough, you get the ultraviolet. If you have an oven, now the ovens that I cook with, you turn them up to 350 degrees centigrade. That's, since room temperature is 300, when I'm going to the oven, I'm basically doubling the temperature. But if you're operating a kiln for pottery, you get up to 1,000 or 2,000, well, more like 1,000 degrees. At that point, you get the same orange glow we saw here. And an experienced potter never has to measure the temperature of their oven. They just look at it. And from the glow, they can tell how hot it is. Not only from the brightness of the glow, but from the color, because the brightness increases very rapidly. And this is anything that is shaking, anything that's hot has shaking electrons in it that emits light. But they can tell the temperature of the oven just from something like that. Now I mentioned, let's see, what are the list of things I have up there? I have, under infrared, I have Osama, I have the tungsten light bulb, I mentioned Mexico. I mentioned dew twice, that's interesting, mosquitoes, global warming. Let me come back to some of that, because we've been on infrared for a long time. Infrared radiation is responsible for what we call global warming, and that is a big issue in the newspapers, and I'll be coming back to that in a moment. But let me jump to ultraviolet, because we have all these pretty things here. Oh, actually, before I do that, there was one demo I didn't get to do last time. If I could have the lights off. All the lights off, please. Okay, so here we have the cross polaroids. Remember that? And then I can put things in between, and some of these things tend to rotate the plane of polarization depending on the stress. So if I stress it, by squeezing it, the light that comes from the bottom Polaroid gets rotated by the piece of plastic and therefore gets through the upper Polaroid. And I wanted to do this. Here's a piece of unstressed plastic. Boy, that has no effect at all. If I undo this, you can see the plastic's there. But it doesn't rotate anything, just does absolutely nothing. It's a nice piece of just gentle, soft plastic. And I get some stressed Scotch tape here. And because it's stressed, the polarization rotates. The amount it rotates depends on many things, but there it is, see? Nice and rotated. Put another piece on top of that. Depends on how thick the tape is. So where the tape is extra thick there in the middle, it gets rotated completely 180 degrees, and so it doesn't get through anymore. But the tape will rotate different colors, different amounts once it gets thicker. It always rotates different colors, different amounts, but it's a small effect because the colors are fairly close in frequency. So I put them closer like that. And now I begin having some fun because I'm getting some of the colors in there. And as I rotate that, the colors will change. Whoops. I'm accidentally taping it to the Polaroid. And I get to feel like this tape, I get to feel like I'm Jackson Pollock here, throwing down colors and using my superior sense of design and color and beauty to come up with a true work of art. Okay, lights back on. We'll have an auction of this work of art after class for those of you who want to donate money to charity. One other thing I wanted to show, And this is, I meant to show this last time, so this is recouping. Light, when it passes by a corner, will tend to bend a little bit. And normally you wouldn't see that, except there's the black of the corner, and there's the light there, and the light that bends a little bit, and some of it bends more, and some bends less. And you wind up getting patterns because the light that bends more can interfere with other light, and light that's bending less will, and so you get these patterns of interference. And I just thought I'd show that here. When light passes by a small object, let's have the lights off again. And over there is going to be the shadow of a bunch of small objects projected on that screen. And what do we have here? We have, that's just a tip of a nail. Let's see if I can turn this up a little bit, see the actual tip. What I want you to do is look at that and look at the shadow. Look at the very edges of the shadow. And you'll see that there's sort of a pattern there of dark and light regions just barely around the edge. I could point to it with my laser, but I'm afraid my laser, my green laser is so bright that it will blind you in this darkness. Let's see how it works. So there's the thing. And then around the edges, there are some really close together lines. Let's look at some other objects I have here. There, that shows it really nicely. Those are interference patterns. Not so important that you know the word, but I want you to know that those come about because light is a wave. And as it goes around the edge of an object, it goes around, as it bends around, sometimes it interferes with itself and gives you a black band like that. This is the edge of a razor blade. And that's a little bit harder to see right there. I don't think that's the most dramatic image. But this is not some, and now there's the head of a pin. And again, as you look at the corners, it tends to be the place where you can see it best. The calculation of those patterns, there's a nice region right there where you can see the dark bands, is actually, you know, it's the sort of thing we have physics majors do. I'll put lights back on now. And if you have the edge of a pin like this, some of the light that's coming here, if you look at it from, how do I want to look at this? Let me put this up now. If the light is coming this way, and here's the sharp edge, some of the light here will come straight. Here there's no light, so you'd expect to find a shadow, and this is all very bright. There's the shadow. Except the light coming here tends to bend a little bit. And the light here bends a little bit. And at certain regions here, the bending light exactly cancels and you get a dark spot. And then over here, they won't exactly cancel, you get a bright spot. So that pattern that you get comes about because of these different amounts of light bending. This is actually a fun calculation for the physics major to try to do these things. It's actually not that much fun, but we do it for them. And calculate those patterns. And that's an indication. Those patterns, those lines that you see on the shadows, are an indication that light is a wave. You can see these yourselves when you're out in the street. I mean, I show them you here, but my favorite place is at night when you see some of these lamps. The sodium lamps are particularly good ones. These are these lamps that are a little bit yellowish in color, and they're very bright, and they use them as street lamps. And if you make a little hole with your fingers and look at them, you'll see the same kind of shadows on them. You can see these yourselves, and those are the diffraction patterns, the interference patterns that you get from the fact that light is a wave. So I can turn this laser off now. Let me get to this, because ultraviolet and infrared are two aspects of invisible light. We're going to talk more about them next time. This is a very wealthy subject. It's a rich subject. It's full of useful, fascinating things, extremely important in modern technology, and used all over the place. As I mentioned last time, these LCDs are used for your LCD screens on computers by electronically switching them. They turn your computer screens on and off. They're used for electronic shutters in your digital cameras. I can get this shutter on and off by rotating it. So you don't see me, you see me. Don't see me, see me. But you can get that same pattern electronically by electronically rotating it. The thing that is electronically rotated is called a liquid crystal. What you do is you really turn this on and off by putting an electric signal on it, and that can cut off the light for an electronic shutter. ultraviolet radiation. Now we're talking about the high frequency end. We're talking about the stuff not over here where the infrared is, but the stuff that's over here. Now, where do we get it? You could heat something up to tremendously high temperature. That's not a good way to get it. So we usually get it from a different means. In fact, it turns out that fluorescent light bulbs naturally produce, because of a quantum mechanical effect we'll talk next week, they produce intense ultraviolet radiation. In fact, all these light bulbs are producing ultraviolet radiation. You have these hollow tubes, and they have a long electric discharge in them. This is how a fluorescent tube works. You get the electrical discharge in here, and because of a quantum mechanical effect that we'll talk about next week, they don't emit visible light, they emit ultraviolet light. So here you have ultraviolet light being emitted in all directions, UV. Ultraviolet light, it's invisible. So what use is this? Great at a party. Halloween party. You put up these ultraviolet lights. They're called black lights. Why are they fun? Well, because when a black light hits your clothing, it will make it glow. Why is that? Again, this turns out to be a quantum mechanical effect. The energy is absorbed into the atoms. The atoms go into what we call an excited state. We'll talk about that next week. When they re-emit the energy, certain materials will re-emit it in a visible color. Very useful for identifying rocks. This is one of the more peculiar uses of it. This is laundry detergent. So for a fluorescent bulb, the way a fluorescent bulb works, this is not a neon bulb. Neon bulb is different. Neon bulb, it actually emits red light. But a fluorescent bulb, what it does is it emits ultraviolet light. Then on the surface of this, they put a material that glows when it's hit by ultraviolet light. And there's a whole industry designed to making a material that will give a pleasant light, a pleasant color. They'll mix in phosphors. They'll mix in red and green and blue to try to make something that will make a pleasant light. You go to the store and they'll ask you, what color fluorescent light bulb do you want? Because the initial ones were what people call very harsh. They had very little red in them. Then they had daylight bulbs. And these are bulbs where they mix in the phosphors to try to get a color that will resemble daylight. They have ones that are designed for your bathroom. So they have more red in them so that you look healthier when you look in the mirror. And they do that by adjusting the materials. They'll have some red, some green, and some blue. This is the most amusing one of all. Ordinary laundry detergent. Look at that glow. I mean, that's really fun. Anybody here have a nice white shirt? You have a nice white shirt. Could you come up here for? No, yeah. Could you? Yeah, no, yeah, Victor, come on. Come here. Let's see. We'll come over on this side. And we have lights down. I just want to see how this works. Okay, nice glowing white shirt. Notice it glows colors similar to the laundry detergent. Thank you. What's going on here is actually one of the cleverest things that the laundry and white shirt industry has ever done. And it goes back to when I was a kid, and there were these advertisements of our laundry detergent will get your laundry whiter than white. I was a physics major at the time. And I said, that's ridiculous. There's no such thing as whiter than white. I'm a physics major. I know better. I was wrong. You can get something whiter than white. How do you do that? Well, you get something which is absolutely white. And what that means is you go out in sunlight and it will reflect every little bit of light that comes off it. That's white. How can you possibly get whiter than that? Well, physics majors aren't always that smart. Some people in the laundry industry are smarter. What they do is the following. Light bouncing off this shirt is not just the visible light, but there's also the invisible ultraviolet light hitting the shirt because the sun does emit some ultraviolet light. And I don't see that. So what they do is they add a phosphor, like the fluorescent bulb phosphor. And they put that into the clothing. And now what happens is I put this in the sunlight and I look at it and say, wow, that's really bright. And it is, because I am seeing not only the reflected sunlight, but I'm also getting the invisible ultraviolet light turned into white. So if I compare this to something that's just plain white, this one will be brighter because of that little bit of glow from the sun's ultraviolet. Next step, convince those who do the wash that brighter means cleaner. How do you do this? You do this with skits. You have, back in the 50s, there was Housewives that they did skits on. Now they're more sensitive to this. They know that men do this stuff too. But back then, they had the Housewives. And the Housewives would say, they wash these things in these 2 laundry detergents. I love this thing, a housewife being an experimental scientist who's doing 2 different detergents just to see how they work. And they come out. And then the guy comes on. It's always a man in those old movies. And he says, okay, lady, take them out into the sunlight. You see a difference now? Oh, yes. This one is much brighter. You know, implication being that it's cleaner. It's not cleaner. It has residual laundry detergent in it. It has a paint that paints the clothing with a phosphor that makes it glow in the sun's ultraviolet and makes it bright. Basically, every white bit of clothing made in the United States. Oh, that's brilliant white up there. The sweater that just is shining white. These things have, and they're over there, these things have this phosphor in them. There's another white. Oh, there's white all over around here. Come up to an ultraviolet or a black light. You can buy these black lights, by the way. What a black light is, there are 2 types of black lights. There's the ordinary incandescent black light. I got one of these when I was a kid. It was terribly disappointing. What it is a ordinary light bulb that's painted black with a paint that lets the ultraviolet come through. This hardly works at all. It's a terrible black light. Never buy any of these. They are a total waste of money. Remember the spectrum. I have it drawn over there. Here's a tungsten light bulb. It looks like this. So here's the infrared. Here's the visible. Is there any ultraviolet out here? Yeah, there's a tiny little bit of ultraviolet. So tiny as to be virtually worthless. But if you paint it black so none of this gets through, that's the only thing that gets through. This thing gets really hot. If it's very little light, never get one of those. You'll find them cheap in some stores. What you want is an ultraviolet lamp that doesn't have the phosphor on it. So the ultraviolet light comes out. Now, ultraviolet light tends to be blocked by glass. So they have to use a special glass so the ultraviolet light really does get out. When you have sunglasses, you may see protected from the UV. These days, essentially all sunglasses, except for the very cheapest, have a little label on them that say protected from ultraviolet radiation. What they do is they just make them out of a glass that absorbs the ultraviolet. Why do you want to do that? To protect your eye from the little bit of ultraviolet radiation that comes through. Particularly important when you're looking at an eclipse of the sun. Your eye doesn't sense that there's ultraviolet radiation coming through, but the ultraviolet radiation has sufficiently energetic wave packets, remember that? We're coming to that next week in quantum mechanics, that it can damage your DNA and can damage your cells. It can give you, it's the ultraviolet radiation that gives you sunburn. It's also the ultraviolet radiation that gives you windburn. I don't know how many of you have ever heard, who has heard of windburn? Raise your hand. Windburn is when you go out there and it's a nice cool day, but you wind up coming back red as a beet. How did that happen? Well, the way it happened was the ultraviolet radiation, which is what gives you sunburn, was just as intense as ever. But the ordinary sunlight didn't get through the clouds so much, it was blocked, so you didn't feel the heat. And if the wind is burning, it's even worse. Because the wind will make you feel cool, and you won't realize your skin is being damaged by the ultraviolet. It's called windburn, but it's not the wind that's doing it. It's the wind that's cooling your skin so you don't realize you're getting hot. You sense the heat from the visible and IR, but it's the ultraviolet that gives you the sunburn. If they come together, then you know, I don't want to be out on this hot day. But if it's blowing out, or the visible and infrared are blocked by clouds, but the ultraviolet is still coming through, then you can get the sunburn without the sensation of heat. So it's called windburn, and people will tell you, oh, windburn, that's even worse than sunburn. Well, it's the same thing. It's just that you don't notice it. So the ultraviolet radiation does that, and the sunglasses that you wear. If you're looking at an eclipse of the sun, normally you don't look at the sun because the sun's too bright. It hurts your eyes to look at the sun. The sensors in your retina get this intense light, and they say, close your pupils and close your eyes. This is bad for you. But if you're looking at the corona of the sun, that is, the main part of the sun is blocked off by the moon being in front. And all that you see here is the glowing atmosphere of the sun. The glowing atmosphere of the sun actually has a very intense ultraviolet region and doesn't have much visible light. Again, this is a quantum mechanical effect, but it also is related to the very high temperature of the corona. This is super hot, hotter than the surface of the sun. So you wind up getting a lot of ultraviolet radiation in this region. And if you look at that, you say, it's not that bright. It's really pretty, but you're getting this ultraviolet radiation. So you want to block that somehow, because you're not seeing it anyway, and yet it can damage your retina. This is the danger of looking at an eclipse of the sun. Actually, I don't believe it's bad to look at an eclipse of the sun for short periods of time if this is totally blocked. You don't want to really stare at the sun when you still have some bright spots showing around the edge of the sun, because that's very intense. But the corona itself is something that I would look at for a few seconds, or you look through a piece of glass, or through a pair of sunglasses that say UV protection, because they block the ultraviolet. I once had a UV meter, and I turned it on in sunlight. There's no reading. Was it broken? I just bought this. Measures UV. Read 0. And I realized, oh, maybe I should get out of the car. I just purchased it. I was in the car, sat down, eager to open it up, make it work. But I was in the car, and the light was coming through the window of the car. I took it outside, big, strong signal. Ultraviolet light. I mean, windows are, thick glass is black to ultraviolet radiation. What do I mean by those words? It's not black to visible light. We use this term black to indicate when a certain color of light can't get through. We say it's black to that radiation. And for ultraviolet radiation, that is the case. Remember, the ozone layer blocks the ultraviolet radiation, not all of it. If we blocked all of it, we wouldn't get sunburn. If it stops blocking, then the ultraviolet radiation on the surface of the Earth will get much worse. Why do we worry about this? The history is really interesting, and it was about, 15 years ago when people began to measure the ultraviolet radiation reaching the surface of the Earth, and they discovered there's a region in Antarctica where every spring is what's called the ozone hole, a region above Antarctica where the ozone is decreased because of chemical effects that are going on. It was a physicist, a chemist at Berkeley who predicted that we might wind up losing the ozone layer because of a chemical we were using called Freon. Freon was sort of a nice chemical. I used to use it to wash my hands. I used something called Freon 11, which was a liquid. It would evaporate very quickly. It was very good at dissolving grease. It's part of a class of things called the chlorofluorocarbons, C-H-L-O-R, chloro for chlorine, fluoro for fluorine, carbons. And these were very popular. They are very nice chemicals because they really don't react with very many things. They're very inert chemicals. They were used in refrigerators as the gas that would be expanded by your motor to make the refrigerator do its cooling. They would use Freon. Anyway, the Freon gets into the atmosphere, and it doesn't react with anything. It's inert. It doesn't react with the oxygen and so on. And so we were building up these Freons in the atmosphere, very small levels. But we're building up in the atmosphere. And they spread out through the atmosphere. They gradually drift to higher altitudes. They get up into the ozone layer. Once they get up, and the ozone layer, remember, is the layer right at the top of the thunderclouds. So you can see where it is. You look at a thundercloud that's growing up. When it reaches, when the top is at the ozone layer, when it gets up there, the ultraviolet radiation can break this thing up. And you get out two bad things then. You get out the chlorine and the fluorine. Chlorine is Cl, fluorine is Fl, I think, on our periodic table behind that screen. Chlorine and fluorine in the upper atmosphere, it turns out, have the effect that when they come into contact with ozone, they cause the ozone to react and become ordinary oxygen again. It's called a catalyst because just the presence of this thing causes the oxygen to react with it, then it comes back, and the chlorine is left behind. You wind up destroying the ozone. So here's the key thing you need to know. Chlorine and fluorine in the upper atmosphere destroy the ozone layer. Now, we're only emitting small amounts of this, and so, hey, why worry? And minuscule amounts of this get into the upper atmosphere, but there's not that much ozone up in the upper atmosphere. It turns out it's a tiny amount that actually protects us from the ultraviolet radiation. So the worry was that this would somehow cause an effect and we would lose our ozone eventually. But a lot of people didn't take it seriously until the discovery made, I don't know, 15, 20 years ago, that the ozone was already being destroyed over Antarctica. This is only in the spring. And in the spring, this hole would develop. A hole meaning that the ozone was everywhere over the whole globe, except there was much less of it over Antarctica. And this was a mystery because the prediction was that this hole shouldn't develop. And then people discovered that the chlorofluorocarbons were far more effective over Antarctica because of a certain type of nitrous oxide crystal that formed at the high altitude there. And on the surface of this crystal, the catalyzing effect of the CFCs, the Freon, was much stronger. Here's what I want you to know. I want you to know that Freon and the other CFCs used in refrigerators and air conditioners, when they get into the air, tend to destroy the ozone layer. That this was observed above Antarctica because of a special condition over Antarctica that doesn't exist most elsewhere in the world. That people get super worried about this because nobody predicted the ozone hole would appear over Antarctica. The reason it appeared was because of these crystals that nobody even thought about having an extra effect that would make the effect much stronger. So people say, God, if something like that happens, who knows what else is up there? We are introducing enough Freon into the atmosphere that it's already having an effect at one location. Now, some people say, okay, but that's Antarctica. Who cares? It's only a bunch of penguins. Well, it turns out that the hole isn't even where the penguins are. It's too far deep. It's not affecting any living creatures as far as we know. So why worry? The people who worry come back and say this is an indication that we have introduced a pollutant into the atmosphere strong enough to have an effect that we didn't predict. We don't want to take any chances that this will occur elsewhere in the world where it will really destroy life. This is the story. The result of the world community is that we outlawed the use of Freon and chlorofluorocarbons in refrigerators and other major uses in air conditioners. Spray cans used to contain these things. No longer. They're outlawed. You may have people who tell you, don't use spray cans, they're bad for the environment. The reason they tell you that is that 15 years ago, they were bad for the environment. This is a remarkable case where the world community has actually gotten together and banned these chemicals. And so they're now used only in tiny specialized cases. They're not widely used. And yes, you can use spray cans, and you're no longer using these chemicals. It's okay.